Okay, so I did my lab on kinetic friction when, like, as a function of velocity, basically. So, um, why did I do that? So obviously the kinetic friction equation is supposed to be mu k times Fn, but I thought that if you were pulling something across a table or a surface or whatever, then at higher speeds they would be the particles in one object would be touching the other particles for less time, so they wouldn't have as much time to get stuck on each other. And so, but then somebody else argued with me that then over any set time period, like if you say 1 second, then the object would be touching more particles than the other object. So I don't really know how it changes or if it's even affected by velocity, but and then also when you're supposed to, you have one equation for static friction, one equation for kinetic friction, and it's supposed to just jump down instantaneously, and that's obviously not possible. So I wanted to see what was going on with that. So my hypothesis was basically that when you increase the velocity, when you're dragging two things across each other, that the force of friction will decrease when the velocity increases. So basically to do this, I had to get a bunch of different materials of different surfaces and different weights to change the normal force and stuff. And so yeah, I went to Home Depot and they have a ton of free stuff, so because they're trying to throw it away. And then I used an accelerometer because that way I could measure the acceleration and calculate the velocity from that. And then yeah, so that's what I did. And I'm sorry, these are really bad pictures. There's really bad lighting. But so basically I had one mass here and one mass there. And there was a pulley. And then I just kind of let go of this first mass, and the second mass would pull it down. And so I did it on different surfaces. And I had a pretty small area to do it, so that kind of caused error. So this is what it looked like. So this is when it was at rest, and then the object would start to move. And this is the graph of acceleration over time. And so I was really confused because it looks kind of like a sine wave, I guess. And I had no idea why that would happen. And then Dr. Schuster suggested that it was because the second mass was swinging back and forth as it's falling. So that was really annoying because I didn't really have any way to stop that. And so I just it kind of affected my data. So once I got the data for acceleration, then I calculated velocity, which is just the integral of acceleration. And then I made this really confusing equation for the force of friction, over at each point. And so it's basically just the tension minus the measured force minus the drag force. So that I wouldn't be getting other forces in the way when I was trying to figure out what was going on with the friction. So this is what it looked like once I added other stuff. And it looks like these are just mirror images of each other, but the red is the acceleration, and it's actually has more amplitude than the green, which is the force of friction, and then the blue line is the velocity. And so again, everything has the sine wave in it, which is really annoying. So I just had to imagine that it was kind of in the middle of it, because that's where it should be if the mass was just straight down. So I wanted to make an equation that would describe what was going on there with the friction. And I wanted it to be dependent on velocity. So I tried graphing things to see if they were linear, basically. And I tried graphing frictional force times velocity because I thought it was an inverse relationship. And so if the velocity was, then it would be dividing over 1 over velocity. And I kept them both over time because everything was a function of time. And if I had just graphed the friction over 1 over velocity, then it would have been values from when it was still and when the equations didn't work, because the equation for friction only worked when the object was moving. And then I found that it wasn't inversely proportional to velocity, it was more inversely proportional to the square root of velocity. So, yeah, and then I wanted to make an equation that would apply to all of them, so I took the average of all those slopes, and it was 0.6688. And so this is what it looked like when I did the linearized graph of friction times the square root of velocity. And I don't know, this one looks kind of like it's not linear, but the other ones mostly did. So, yeah. So that didn't really work because the line of fit for the force of friction works like really good for some of the graphs and really terribly for others. So I realized that what I'd been using as a constant, which was the slope, was actually a variable, which makes sense because why would they all have the same constant? Because that would imply that like the velocity, anything with the same velocity would have the same force of friction. So that was really dumb. But so I figured out that the variable depended on the like surface of the two materials and the normal force and how fast they were accelerating, I guess, in the gravity. So then I got a lot of my graphs that had like really crazy slopes be a lot more linear, because like this seemed really linear, but the slope was 0.2269, and the slope that I was using as the average was like 0.66 something. So it wasn't really working, and that was how the original fit was fitting, and it's like obviously not following the data is the green curve, and it like doesn't match at all. So I redid that and said that S was a variable, and I found S for each of the graphs by using just their slope. And so I kind of took out the original like UK times Fn because I didn't like take out Fn for every object, and obviously that's a constant for each object. So I could have and then made it like a more complicated equation, but I didn't really need to because it was just showing the same like phenomenon happening. So after I changed to a variable, a lot of the graphs worked a lot better, and yeah, that was just saying that it was being dumb. So what was happening was I'll just show it. So on some of this graph worked really well. So the purple is what the force of friction should be according to my equation, and the green is my measured data. But on some of the graphs, it wasn't matching up until the end, but they all matched up until the end. So I'm really not sure what happens at the beginning with some of them, but I think it might just have something to do with when it's changing from static to kinetic. And also everything's averages. So the really light objects, and I think there's one on the next slide, like they still didn't fit at all because they had such little friction that it was just down at 0, and this curve was always like a curve that started from really high. And yeah. So another problem that I had with it was that since I had those sine waves, it was really hard to find a best fit line without like feeling like I was like reading the data. But I mean, I wasn't. It was just that my data sucked. So yeah, so this is for styrofoam, which is really light, and the purple line, like my projected line, is way higher than the actual data. And no matter what I did, I couldn't really get rid of that. So I had a lot of error because I had a really short surface, and so that's why for some of them, like I would only get through like halfway of a sine wave, and then I really didn't know what that meant because I couldn't see like an average. And I had to take averages for all my lines and everything because things were swinging back and forth. And I had 24 trials, so I only did like one for each combination of like the object and the surface. So that might make it easier if I had time to do lots. So I think the equation that I found with the force of friction equals S over the square root of velocity is still like pretty approximate, just like the one that doesn't depend on velocity is. But I think that it shows that it has some kind of effect. The velocity has some kind of effect on the kinetic friction. And somebody suggested to me that maybe the reason that decreasing is not just because it's like doesn't have time to grab on, but maybe there's like air getting in once it starts to go really fast, like it has like lift. But I don't know, and I don't really have any way to test like how, like why that's happening, because it's really small and I can't see it. So yeah, that's it.
Put it in a vacuum, right?
Yeah. I don't have
Question? I was struck by how you came about it with a very fresh approach. As you were getting into the differences, you know, a different slope for every one of the surfaces, it occurred to me that you could use mu for the surface. You could just measure mu for the surface and then correct for mu. Maybe there's an underlying theme. If you knew mu for everything, what the correction would be.
Well, I wanted to do that, but I didn't have. I think that if I had a really long surface and I could let it level out, because the graph, I don't know how to go back on here, but it's like really slopey at first and then it kind of levels off. So I think that's probably why the standard formula works, is that it like kind of stays around one number. But I didn't have anything to compare it to, because then I could have done error analysis, but I didn't, or error calculations, but I didn't because I didn't know what I was looking for, like having to compare it to at all. But yeah, I wish I could have done that, and also like found what the different components of the variable that I found are, like how it relates to the normal force and stuff.
You could definitely go further into this. It's really interesting. One more thing, Allie, is the sine wave thing that person suggested. Did you get a video of it doing that, or did you notice that it was doing that? Is it real?
I mean, I think it really was doing that only from like those pictures that I was looking at. I was like, the problem is I just tied things to like the objects. I just tied string around them, so they were kind of like tilted, and I don't know what they were doing. I didn't really like expect that to happen. So.
And then you noticed it afterwards when you looked at the data after all the experimenting. Yeah.
Well, I noticed it when it was happening, and then I was just really confused and thought that like the accelerometer wasn't reading or something. So yeah, so that was like really annoying the whole time, because I was just like staring at the data and I was like, I don't know what's happening. But then I think like I ended up just looking at where like the like middle between the two crests of the wave.
That makes sense.
And I think it wasn't that, like, I think I would have gotten the same data if it hadn't been swinging, but I would like to actually have seen that, because I don't like trust that it would have been the same.
Right. Thank you, Allie.
Okay, so I did my lab on kinetic friction when, like, as a function of velocity, basically. So, why did I do that? So obviously the like kinetic friction equation is supposed to be mu k times Fn, but like I thought that if you were pulling something across a table or a surface or whatever, then at higher, so basically I had one mass here and one mass there, and there was like a pulley, and then I just kind of let go of this first mass, and the second mass would pull it down. And so I did it on like different surfaces, and I had a pretty small area to do it, so that kind of caused error. So this is what it looked like. So this was when it was at rest, and then the object would start to move, and this is the graphic acceleration over time. And speeds, they would be like the particles on one object would be like touching the other particles for less time, so they wouldn't have as much time to like get stuck on each other. And so, but then somebody else argued with me that then over like any set time period, like if you say 1 second, then the object would be touching more particles of the other object. So I don't really know how it changes or if it's even affected by velocity, but basically to do this, I had to get a bunch of different materials of like different surfaces and different weights to change like the normal force and stuff. And so yeah, I went to Home Depot and they have a ton of like free stuff, so because they're trying to throw it away. And then I used an accelerometer because that way I could measure the acceleration and calculate the velocity from that. And then, yeah, so that's what I did, and I'm sorry, these are really bad pictures, there's like really bad lighting. But, and then also, like, when you're supposed to, you have one equation for static friction, one equation for kinetic friction, and it's supposed to just like jump down instantaneously, and that's obviously not possible. So I wanted to see like what was going on with that. So my hypothesis was basically that when you increase the velocity, when you're like dragging two things across each other, that the force of friction will decrease when the velocity increases. So,